segment 2 of chapter 5, nuclear radiation. So we were talking about half-lives and how to do a half-life calculation, and we left off talking about exposure and safety. So that's where we're going at next. So factors that influence the degree of exposure. Obviously the magnitude of the half-life, that's what we were just discussing. So the shorter the half-life, the faster things decay, and that means more damage. More particles are coming off at a faster rate. Another thing that will influence your degree of exposure is your shielding. And of course, you know, if you've ever gone to like the dentist and you get your annual x-ray done of your mouth, they put the huge lead vest on you. Or if you've ever broken a bone and you've been in the ER, they'll put like a lead blanket over top of certain areas that are going to be underneath the exposure but don't need to be exposed. So shielding, right? We can provide protection from the radiation. And then of course there's the type of radiation. So alpha, beta, gamma, some are worse than others. And then of course, last but not least is the area, right? So in other words, having your hand exposed versus your brain, right? A little bit difference there. So shielding and the types of radiation. So alpha particles then, do we need to worry about alpha particles? And the answer really is no. So alpha particles are actually stopped in 1 centimeter of air. So if I take my alpha producing stuff here, I don't know, take this packet and I put it right here in front of me, then I'm good. This is more than a centimeter between it and I should be fine, right? So that's because that particle is big, it's bulky, right? It's like the 18-wheeler and it's got no energy going behind it. So it just slows right on down and comes to a stop. Beta particles. Well, beta particles, if I want to deal with beta particles, what I can do is go downstairs, crack open a seltzer water, suck that thing down, and then put my thing right inside because it only takes 1 millimeter of aluminum to stop a beta particle. So again, not a whole lot going on there. Last but not least are gamma rays. Now gamma rays are the worst, right? Remember, they're not stopped by charge and they're not very big. So they move fast. They have lots of energy because they are energy. They're not attracted to anything and they're small. So boom, all kinds of penetration, all kinds of damage. You need concrete or lead to provide an adequate protection. So an X-ray is right up there with a gamma ray. That's why we have the lead blankets when we're looking at X-rays, right? So X-rays, same as gamma rays, high radiation. All right, so what's the impact then? What are some of the health effects? Well, first we have 2 types of health effects, right? We have somatic, which is whole body damage. So this would be things like that are chronic, like cancer, or to be acute. And we're going to talk about that. We're going to talk about acute radiation syndrome. This is just me, the person getting sick from the radiation, somatic. There's also genetic damage. So genetic damage can be done. This is going to alter your genetic material. And of course, then you're going to pass that on to your offspring. So it could lead to a mutation. So we're not going to get into a lot of the genetic components of it, but we are going to look at the acute radiation syndrome. This is what you'd most likely experience if you were always working with X-rays, gamma rays, or some other form of radiation. So the first thing we look at is the LD50. So the LD50 for people is 400 to 500 rem. Now, if you don't know what an LD50 is, that's the lethal dose for 50% of the population. So half of us would be dead at an exposure between 400 and 500 REM. So if you're below 100, there is no significant sign. And this is our everyday world, especially in Delaware in the summertime. You're below 100, but you are being hit with radiation, right? And if you've ever been out on the beach in the summer, you know, not only do you get sunburn, but you get UV rays. So you're being hit with radiation, right? So that's our normal, below 100, but above 0. Now, 100 to 500, this is a 50% survival rate area. You have a loss of hair and your blood chemistry starts to alter, right? So this is chemotherapy is what that is. So if you've ever met anybody or known anybody to be on chemotherapy, you know that they're always doing blood work, like weekly, sometimes even more often than that as they're adjusting the drugs, trying to make sure that the blood chemistry is where it's supposed to be. Now, this is also going to be an additive effect, right? So as we increase the amount of REM. So here we go 500 to 700, you notice you get all the earlier effects. So your blood chemistry is already being altered. Your hair loss is already going to happen, right? Now what we're going to see is the destruction of bone marrow, the loss of red blood cells, white blood cells, and platelets, and now you are going to die within 36 days. So the majority of people, once they're exposed to 500 to 700, it's going to be death. Right? It's not going to be a reversible effect here, especially once we destroy the bone marrow. So once the bone marrow is destroyed, we can no longer make platelets, which means we can no longer make red or white blood cells. From 900 to 2000, you get vomiting, diarrhea, and now infections will start to set in. You can't defend yourself is what it comes down to. Your white blood cells are gone. They've been diminished. You're now going to die within a week. So the bright side is you're going to die a little sooner. So rather than being in agony for 36 days, now it's only going to be 10 days. As we increase that level, you see 5,000 now, death within 3 days. And again, you get all the earlier effects, but now we're getting to a radiation level where there's going to be a heat component, and we're going to start to feel third-degree burns. At 12,000, we're now down to hours, and now we're going to have severe bleeding and fluid loss. So at this point, we're basically being blown up, and all of our fluids are starting to come out of us. Okay? Now, this is not a nuclear weapon at this point, just so you know. A nuclear weapon is going to be on the order of hundreds of thousands of REM. So it's going to be complete vaporization of most biological material within seconds. And then you're talking about as it expands out, the REM values will go down, and you'll get to a place where you're in a fallout area, so where you'll start to experience some of these effects, but not full-blown death. Now remember, we said at the beginning between 700 and 900 you were going to die, and we said that was due to the blood chemistry. So for the blood chemistry, this is why you're going to die, right? First, we have our white blood cells. They're our little troopers. They're going to go out. They're going to see the cancer as being not natural, something that has to be destroyed, and so they're going to go after it, and of course they get beat down really quick. The platelets are next, right? So the platelets, they're just kind of flowing around, and they're getting beat up. Of course, once the platelets are gone, we can no longer manufacture our red blood cells, which means now we get an extra day or two before they're all gone. So when we think about nuclear radiation and we think about death and these types of things, it makes us wonder why. Why do we care about radiation as far as what use and what value could it possibly have? Well, there's plenty of uses for radionuclides. Our ability to measure radioactivity is going to be very sensitive. So as a result, there's a lot of uses for it. Of course, in addition, its interaction with living matter can also be exploited. So what are some of those uses? Well, there's dating techniques, carbon dating, for instance. When you think about the amount of radiation that is in the carbon, it's not that carbon dating. You remember the half-life was 5,730 years. And so what we'll do is we'll look at the amount of carbon-14 that's in a sample versus the amount of carbon-14 that's in our material that we want to test. Depending on what that difference is, we'll look at the half-lives being 5,730 years per half-life. And that's how we date things back so far into past. There's also cancer treatment, right? So not only does the radiation known to cause cancer, we can actually use the radiation to defeat cancer. And then of course there's tracers. So we can use it to trace like mapping for rivers, waterways, environments, things of that nature. And we can take that to even smaller, the human being, right? By looking at imaging. So we can image like what's going on with your digestive tract if you have issues, what's going on with different parts of your body based upon just computer imaging and looking at those active notes. And then last but not least, testing methods. So we can test water and things like that using radiation. Now again, for us, most of the students taking 110, you're going to be going into some sort of medical application. So we're going to kind of focus that here. So we're going to look at cancer therapy. Radiation can both cause and treat cancer. So radiation causes molecules in the cell to break apart. In other words, we ionize them. So if you think about it, what we're going to do is we're going to take a cancer cells and we're going to smack them with radiation. They're going to then break apart and not be able to reorganize, right? That's the goal. So the most significant damage is done when DNA is destroyed. So when we can destroy the DNA of the tumor in this case, then it can't replicate. If it can't replicate, it can't grow. And of course, if it is growing and we can affect those cells, then we can have the greatest effect in the rapidly growing cells. So we can use radiation then to treat cancer, just like radiation does cause the cancer. Now, some potential ways to do this would be bombardment. So we can use cobalt-60, expose the area to gamma rays. There could be implants. For instance, thallium wire is used in the treatment of eyes. Cesium, if you're going to use the balloon catheter for the bladder. There's also interstitial therapies. So for instance, we can inject gold directly into a tumor. There's also internal radiation. We'll ingest iodine, and it goes right to the thyroid. Now, we can also use radioactive isotopes as tracers, right? Again, because our ability to measure radiation is so sensitive, we can introduce a small amount of radioactive material and see where it goes in the body. This is your GI soda, right? It can be used to measure small amounts of chemicals in the body like hormones, where we do a radioimmunoassay, right? Where we take iodine 127, we can trace the thyroid function and see if we have tumors, whether it's a benign tumor or whether it's going to be cancerous. So again, those would be some of the reasons why nuclear radiation is sort of worth it. Now, another option would be to look at nuclear power. So power can be obtained two ways. Fission, by splitting atoms, that's where our nuclear weapons come in, but it's also how we use nuclear reactors. What we do is we take the energy by taking a big nucleus and breaking it. The smaller nuclei will be more stable, and of course that's going to release energy. That energy comes off exothermically. We can then harness that heat energy, turn it to turn turbines with steam, generate that into electricity, spread the electricity out across the grid, right? And again, that's what we do in nuclear reactors. Now there's also fusion. Fusion is the joining of atoms. So same idea, but reverse. Now, instead of taking a big nuclear radioisotope and breaking it apart, I'm going to take small ones and fuse them together. And in making them, I'm going to make a more stable molecule. And that way we're going to get energy off. Okay, and that's exactly how the sun works. So I don't know if the videos are going to work. Let's see. It's not looking good for us here. Maybe. Yep. Unfortunately, it's not. Doesn't seem to be working. So what should happen in the video is this one nucleus here would slam into this one, and this would break apart, giving us two pieces, and then typically two of these would also come off, right? And that would be a nuclear fission. So we take a small ion, we smack it into the nucleus of a larger element. It breaks apart into two smaller elements and also gives us back energy. In a chain reaction, what would happen is we would start with that one nucleus. We would hit the bigger nucleus. It would break apart, giving us energy, but also produce two more ions, which could then go on and smack two other nuclei, which could go on and smack two more nuclei, so forth and so on. And that would be called a chain reaction. Now, in chain reactions, if we have a critical reaction, that means we have just enough fissions occurring to keep the chain going, right? So neutrons being formed would equal neutrons being used. And this is the goal behind nuclear power, okay? Now, unfortunately, in our goal of using nuclear power, we sometimes run into a supercritical reaction. And this is when we have an excess of neutrons are being produced and the rate of fission keeps increasing. In other words, more and more heat and more particles are coming off, and it becomes uncontrollable, or maybe it's controllable, but it's designed to do it, and that would be what our nuclear weapons are based on. Now, that's chain reactions, and that's nuclear fission. Okay, so energy from fission then, we take something like uranium-235, we'll use that as the fuel in our reactor. We'll bombard it with one neutron. It'll break apart into krypton and barium, and then produce three more neutrons plus a whole bunch of energy. Those three neutrons would then be used in the same reaction with more uranium, produce more krypton and more barium, giving us more energy. Now, the energy produced by splitting just one atom is approximately 200 million electron volts. Now, that might not mean a whole lot to us, 200 million electron volts, but let's try to give it an image. If you take 100 grams of uranium, and you could use that 100 grams to produce as much energy as 80 trillion tons of TNT. So if you've ever seen like an old Western movie where they take sticks of dynamite and they blow up bridges or blow up mines, or you've ever seen a mining excavation where they use TNT to blow up mines and pull the dirt out, things of that nature, 80 trillion tons of that would give you the same energy as 100 grams of uranium. And that's why we use uranium, right? That's why we use nuclear reactions, because we get a whole lot of energy out of just a little bit of material. Now, we also know that it's very unsafe. We just saw we could have a supercritical reaction. So scientists currently are working on fusion. Now, fusion is when we're going to take two small atoms, fuse them together. It also gives us off energy. And we know that the sun does this. It takes two hydrogen atoms, fuses it, and makes a helium. Okay, so that's currently what we're trying to do. Now, if I take a heavy hydrogen and I mix it with another heavy hydrogen, I can make a helium, get the one neutron, and then get 14.6 million electron volts. Not nearly as much as before, right? Here we saw it was 200 million electron volts. Here we're only going to get 14.6 million. So 200 million, 14.6. However, it will be great when this works because the fuel would come from the oceans. In other words, it'd almost be free. So the process here would be basically taking water, pulling the hydrogen out of the water, making it into helium, giving off a few neutrons, and then giving us energy. So our energy would literally just come from water rather than all the other risk that we would have with all of the other stuff that could go bad with supercritical reactions, meltdowns, and things like that. All right, so that's pretty much it for our nuclear chemistry. And because we've done this unit last this semester, this is also the end of the semester. So there are no more lessons following this one. So I will tell you good luck. It's been a pleasure putting together these videos. Hopefully you're able to use them and you're not having any issues with them. If you ever have any questions, please feel free to contact me at ccaro@dtcc.edu. So even when you move on, whatever the next chemistry course will be for you, if ever, if you run into issues, don't hesitate to come back and email me and ask me your questions. All right, have a great semester. Good luck on the last exam, and hopefully we'll be back to normal soon, and maybe I'll see you around in the hallways. All right, have a great day.